Hello, hello, hello. Welcome, everybody. Hopefully you can all see and hear me. Hello, welcome to our A-level chemistry YouTube class on reactions of alkenes. Please feel free to say hi in the comments. Let me know you can hear me all okay and everything. But welcome. You can see a couple of people already saying hi, which is lovely. How is everybody doing? Are you all feeling good? Welcome, welcome, welcome. So this is our A-level YouTube class on reactions of alkenes is what we're doing at the moment, or what we're about to do. So welcome, please, like I say, please feel free to say hi in the chat. It's lovely to see who's here and who isn't. So hello, hello, welcome everybody. So really nice to see some of you back again. And nice to have, it's always nice to have new people as well. So hello, hello. My chat seems to have frozen, which is frustrating because it was all working a second ago. So that's good. Oh. I think just my Microsoft Edge has just frozen actually. But hello, and anyway, hopefully you can still hear me. Welcome to our YouTube A-level chemistry YouTube class on reactions of alkenes. This is our last chemistry YouTube class before Christmas or for the new year. So we will be doing some more after the new year, but this is our last chemistry class until then. I'm hoping my internet is going to, or Microsoft Edge is going to sort itself out in a second, because at the moment I can't see if people are saying hello or not, but I assume you all are. Oh, it might be sorting itself out. Oh, go on, you can do it. Let me see what people are saying. I think I recognize some names, so hopefully. There we go. Fabulous. It's working. Good. Hello, hello. Hi, guys. So hello, Khadija. Hello, Mushafi. Welcome, Mohammed. So this is technically year 12 content. Am I back? Thank you, guys. Sorry. It had a moment, but hello, welcome, guys. So yes, this is technically year 12 content or first year content. So but welcome. I can see see all my chat now. Yay, well done. So hello. Awesome. So anybody, brilliant. Thank you, Mohammed. That's fantastic. Right, let's get started then, because that means I'm a couple of minutes behind. Sorry about that. Technology is amazing, and sometimes it works brilliantly and sometimes it just has a funny, and it was perfect until I hit go and then it had a funny. But hello, hi Olivia as well. Hi Doreen. Hello Elia. Please, apologies if I say your name wrong, but please let me know if you want me to pronounce it another way. Hello from Pakistan. Very nice. Cool. Fantastic. Right. Hello Matthew. Nice to have you here as well. Let's get going. So this is our A-level chemistry class on reactions of alkenes. So we're going to look today at a bit of alkene chemistry. First of all, I'll just give you a hello from me. So I'm Alyssa. I'm one of the tutors here at SnapRevise. I do our chemistry tutoring. I'm the lead GCSE chemistry teacher and A-level chemistry teacher. I've got a PGCE in chemistry education and a master's in chemistry. So chemistry is kind of the science that I really love, but I also teach all the other sciences as well. And I have been teaching A-level chemistry, science all the way from Key Stage 3 all the way up to A-level chemistry for over 6 years now. So loving it, absolutely loving it. Just so that you guys are aware, we're going to pop this on the end of the PowerPoint as well. But if you wanted or were interested in having a 25% off your first month's subscription payment, then you can use the code BACKTOSCHOOL21. So BACKTOSCHOOL21, all capitals, 21, will get you 25% off your first month's subscription. which is, if you want to come and have a look, see if our courses are for you, then please do that thing. The code we've just popped in the chat. If you haven't already, please download the slides, because A, you can write along with us now, and B, you can use it for revision. So even if you just want to sit and listen, or interact on the chat, you can save these and use them to create notes from later, to revise from, etc. A couple of months down the line. So super, super useful. Okay, Mohammed, that's it's a very broad question, I'm afraid, because it depends what you want and how many subjects, etc. So I would have a look, investigate on the website if I were you, and or send an email to hello@snapprovise.co.uk and chat to them about what you're interested in. The slides should be in the description below, hopefully, if you want to download those. All of our videos should have slides for you to download that you can write on, so please have a look. We're not, we might cover it, I can't actually remember, briefly, so I'm just having a quick flick through. I don't think we specifically look at the reactions of alkenes with water. No, I don't think we do. I'm just double checking. But no, I don't think we do look at reactions of alkenes with water. Okay. Yes, it is, Matthew. Well done. Right, let's have a look. Let's get going. So what we're going to do, hopefully, by the end of this, about 50 minutes, we'll understand the reactivity of a double bond. So how does it react? Where does it come from, etc. We're going to, or what does it do? We're going to recall and draw the mechanisms for some different electrophilic addition reactions. And we're going to look at Markovnikov rules. We're not going to look at polymers, though. So for AQA, just to clarify, we don't call it Markovnikov necessarily in AQA. We call it major and minor products, but it's the same thing. It just has a name in Edexcel. So it's based around all three. So that was the AQA specification points that we're going to be covering. This session intends to cover the specification points from all three main exam boards, AQA, Edexcel, and OCR. That was the AQA, specification points we're going to cover. These are the OCR specification points, and you'll notice they name it as Markovnikov's rule, but it's the same content as in AQA. And then Edexcel, we don't look specifically, or they don't mention specifically a rule, but we do talk about addition to unsymmetrical alkenes over here, which is the same thing, formation of major and minor products. Okay, it is a mix of all three, exactly. If in any of our web classes we cover content that's not covered in one of the exam boards, we normally say so. We try to, to say this isn't, if you're in AQA or whatever, this bit isn't for you or whatever, but mostly our web classes cover all three. So let's have a look then at some EZ isomerism. So this is content that we need to be confident on. Hopefully we already know, because we will have done it earlier on in year 12 maybe, but it's definitely to do with alkenes. So first of all, what is stereoisomerism? What is stereoisomerism? Hi, Hayda. Sorry, you arrived when you wanted to arrive. We have started, if that makes sense. So what is stereoisomerism? What do we mean by stereoisomerism? What's the same within structures that have got stereoisomerism, and what isn't? Mahek, looks like you've got it pretty spot on. So stereoisomerism, oh, that's, yeah, looking good. Fabulous, good. So the one thing that we need to be clear on is they have the same molecular formula. Fantastic. So stereoisomers have the same molecular formula. That's the key point, meaning they're isomers. So same molecular formula. And then the stereo bit, as you guys are hinting at, is they have Yeah, so we've got to be really careful. There's a couple of people who have said different structural formula, but if you were to write out the structural formula of these two isomers in front of us, the structural formula would be identical. So the structural formula doesn't change. Structural formula. It's the arrangement in space. Well done. Good. Lovely. They have a different arrangement in 3D space or just in space. Good. Well done. Fantastic. And it's because of this double bond. Lovely. So we're going to focus mainly on EZ isomerism rather than cis-trans, but I will mention that in a second. So for this EZ isomerism, does anybody know random fact? Yes, you could. Yeah, I've sorry, just to answer that question, could you use the same, could you just say structural formula instead of same molecular formula and same structural formula? Yes, you could. Yep. When we talk about isomers, we focus in on the fact that they have the same molecular formula, I think. So your examiner might be looking for you to say same molecular formula, but the same structural formula is saying the same thing. So that's fine. Yeah, good. So which is which then? Which of these is an E isomer? Which of these is a Z isomer? And how do we tell? Oh, we've got some differing opinions. Okay, so good question, Haydar. What is EZ? So EZ isomerism is a type of isomerism. Isomers have the same molecular formula. In this case, stereoisomers have the same molecular formula and the same structural formula. So they are put together in the same way, but they have different positions in space. And this is, I think somebody mentioned it earlier, because we have got this double bond, it can't rotate. There's no rotation in the bond, which means these two structures are different. They're not the same as one another because these groups have different positions on one side of the double bond. If you want to look at it like that, we have different groups either side. And E and Z is our way of naming them. I used to know what they were called, what they stood for. It's German, I think. It's something, I think Z is like zusammen, which means the same. And I can't remember what the E one stands for. If anybody knows, pop it in the chat. But what they mean is they tell us what these arrangements are. So let's see if we've decided then, guys. Have we? Yeah, so I do the same. I think it was Ikra. I do the same as you. Entingen, that's the one. I can't say it. I'm not going to try. Apologies if anybody speaks German. Entgegen. Apologies if anybody speaks German. Good. So I do the same. I say Z, they're on the same side. So they are both on top of the double bond. So that would be a Z isomer. And then E it's like Entgegen. Entgegen. Thank you very much. Hopefully I've pronounced that a bit better. Hi, Marianne. Nice to see you. So our left-hand one, this one is Z because they're on the same side. And therefore the other one is E. No, you wouldn't, Haydar, not at all. No, this is just to help you put puzzle pieces together in your brain. Rather than just remembering random facts, can you, if you've got other things that you can link them to, other things that you can slot into your brain, then it makes it easier to recall them. So you don't have to know what they stand for in an exam, definitely not, but great question. Okay, so let's have a look then at these differences. So the top two we've just said are, sorry, pressed a button. Oh, press two buttons, get back. So these top two we've said, the top one is a Z isomer. The left-hand one is a Z isomer, and the right-hand one is an E isomer. Z because they are on the same side, and E because they are on opposite sides. These groups. Now, where have we got those groups from? Where did we get those groups from? How did we decide which groups were on the same side and which groups were on opposite sides. Right, what do we look, what rules do we use? Anybody know? Oh, it looks like somebody's might have mentioned it already. I think most people, most people use the Khan-Ingold-Prelog rules. CIP rules, that's it. Good, fantastic, well done. It's the Khan-Ingold-Prelog rules, but it basically we look at atomic number to create priority groups. So really good if you guys have said any of that. We order it in priority using the Khan-Ingold-Prelog rules. Fabulous. And we know that our carbon here has a higher priority than a hydrogen. So we've looked at what this is attached to. The top one, the carbon is attached, the top group, the first thing that it's attached to is a carbon. The bottom group, the first thing it's attached to is a hydrogen, which means the carbon takes priority. It's got a higher atomic mass, and therefore the top group is our priority group, and the bottom group, which is just a hydrogen, the bottom group is second priority, so not priority. And the same on the left-hand side, carbon has a higher priority than hydrogen, therefore top group takes priority. So then we look at what side of the double bond, are they both on top, are they both on the bottom, are they both, or are they opposite? We look at what side those priority groups are. And in this case, the priority groups are on the same side, and therefore that is Z. Because we've got two identical groups here though, what else can we use? What other notation could we use to describe this, this left-hand Z isomer? What other notation could we use? Because we've got two identical groups. We've got CH3 and a CH3, they're both the priority groups. Fantastic, well done. Cis or trans. And in this case, this isomer is a cis isomer. Cis being same, it's a word that's kind of come into common conversation nowadays, but cis being same. So cis, they're on the same side. And so I'm going to put same. So cis is on the same side. That helps us link together those. On this right-hand one, we said that E, and it must therefore be trans. Trans is in opposite, like transatlantic flight, a flight that flies across opposite the Atlantic. So they are on opposite sides. They're across from each other on the double bond. So they are opposites. Okay, but no, good question, Sophie. So what we're just about to look at is how we can use that. So when we come to these bottom two notations, bottom two structures, sorry, if we were to give them a name, we can't use cis trans. Huda, yeah, well, I'll explain these bottom ones and then just see if you're still stuck. Okay, so no, good, well done. Cis is not always the same as Z. If you name something as Z and you know it's a Z isomer, it may not also be cis. So cis is when you have got two groups that are the same. If they are identical groups, so cis and trans, you need identical groups. And you look at where those identical groups are in the double bond. I'm going to just put identical there just to remind us it's identical groups. And the E and Z is just priority. So for these bottom ones, we can't use cis or, we can't use cis and trans. I meant to write both of them. We can't use cis and trans for these bottom two because we don't have identical groups. We've got 4 different groups, but we can still assign a priority. So let's have a go at assigning priority. Yeah, good. I like that, that phrase. Cis trans is a special case of EZ isomerism. Yeah, good. Okay, so in this case then, this bottom left one, let's look at our priority groups. Let's look at the left-hand side of the double bond. Which is priority, the hydrogen or the iodine? In this case, which has priority, hydrogen or iodine? Iodine, definitely, well done, because it has the higher atomic mass. And these are nice and simple because we've only got one atom to look at. So we look directly at the iodine and we say, right, the iodine is higher priority than hydrogen. Okay, good. What about the right-hand side? Which has higher priority, chlorine or bromine? Which has higher priority? I might get my highlighter out, actually. I'm just going to highlight the priority groups here. So here, this is my priority group. So which has got priority, chlorine or bromine? It's bromine. Bromine definitely has got a higher atomic mass. So bromine is our highest priority on the right-hand side of the double bond, and therefore chlorine is second priority. So if bromine and iodine are both on the bottom, then we're looking at our, oops, where's my pen gone? We're looking at our Z isomer. They're on the same side. So this is a Z isomer. Okay, both our priority groups are on the bottom. They're on the same side of the double bond. They're both on the bottom, and therefore it is a Z. Bromine is higher priority than chlorine because bromine has a higher atomic mass. And we look at the bond, the atom that's directly bonded, what's its atomic mass? And in this case, bromine is higher, so that gets a priority. I'll do it super quick on the right-hand side, just because I don't want to spend too much more time on this if we can help it. Iodine is higher priority than hydrogen on the left-hand side of the double bond. And on the right-hand side, or the right-hand carbon, we have our bromine. And in this case, they are across from each other. And therefore, so that's priority one, that's priority one. And because they are across from each other, that must mean this is E. There are lots of different ways to remember this. I remember the same side. And if you say cis, they're on the same side as well. All of that, the cis and Z kind of go together. So I link those two together and I know which one that is. And therefore the other one must be E and trans. Trans, I think it can be easier because transatlantic, you can think opposites. But E can be quite hard to remember. So I remember Z, if I know Z is the same side, then E must be the other one. So do you only get EZ isomerism in alkenes? So yeah, we definitely don't get it in alkanes, good, because we can have rotation around the a single bond. You can definitely get cis-trans isomerism in other structures. I don't think you can get EZ. I'm not 100% sure. I know for sure that we use cis and trans notation in other molecules, not just alkenes. I'm not sure about E and Z. I have nothing springing to mind, but I can't say for definite that you don't. At A level, we don't look at anything else apart from alkenes. Is cis and trans in AQA? Great question. Yes, it is. Yes, it is. I don't know why I'm looking at. Yes, it is. Yeah. What else was I going to say? Yes, good, exactly. Lovely. That's exactly what I was thinking of there. Random facts, exactly right. Isn't it assigned by atomic number, not mass? Yes, it is technically atomic number, but atomic mass is, when we're looking at these, you're never going to be asked to explain that first. Well, I don't think you'd ever be asked to explain that. And it's effectively the same thing, but we're looking at the atomic number of the element directly bonded to the carbon, and if they're identical, look at the next thing that it's bonded to and then compare those. But we're not going to look at anything more complicated than this, I don't think, otherwise we're going to get stuck. So when do you know when to call it cis or Z? So cis, you can only ever name something cis and trans when it has an identical group. So we can't call these bottom two cis and trans at all because they don't have identical groups. With the top ones, you can use either notation. Read the exam question. If it asks you to give cis-trans isomerism or the cis-trans notation, then use cis-trans. If it asks for EZ notation, give EZ. If you're not sure, I would give EZ just because we're more often than not when we're in general laboratory work, we use EZ. But it should ask you in the question it should ask you in the question which one it's looking for. Okay, what I'm going to do, because we are running quite far behind, these are all great questions, but I want to try and press on a little bit. We're going to just miss this slide out and we'll go straight onto our alkene reactivity. So that slide there was just looking at some definitions, but we're going to go straight on to looking at alkene reactivity, just to see if we can push on a little bit. So alkene reactivity, when you're looking at the reactivity of anything, the reaction of anything, any sort of mechanisms, reactions, etc., look at what it is about that molecule that is reactive. And in this case, the thing that's reactive is our double bond. It's our pi bond. Now, I'm being quite lazy in calling it a double bond / pi bond, because hopefully, as we're already aware, a double bond is made of a sigma bond, the single part of a bond, and a pi bond, which is the double part. And it is, of course, the pi bond that is attacked. It's the pi part of the double bond that's attacked, not the sigma part. Lovely. Good luck with that. I remember doing my EPQ. So there's two types of reaction that can happen easily with alkenes that we look at. There's addition. So because our carbons are double bond, they're what we call unsaturated. So our unsaturated carbons can form another bond with other molecules, and that means we get addition reactions. So each carbon can make one more sigma. Oh, that was a rubbish sigma. Sigma, that was also rubbish. Hopefully your sigmas look better than mine. Sigma bond with another species of some kind by breaking the pi bond. And this is an addition reaction. So as in our double bond opens up, it breaks, so that we have two extra species, things, atoms, or groups attached to our molecule, one to each carbon. What type of reaction is in cracking? Good question. We don't have a mechanistic name for it, if that's a word. We don't have a mechanism name for it. I don't think you need to have a name for it. I think it is just cracking, because you break a bond, but you don't add anything in. You're not adding anything, you're not taking anything away when you crack long chains. So it's just cracking. I don't think it's a mechanism as such. It's more like a physical process, I guess, than an actual chemical reaction, even though technically it is a chemical reaction because we're making new substances. But we don't add anything, we don't take anything away. So that's a good question, actually. Oh yeah, of course. What an idiot. Yes, you would call it decomposition because it's breaking down. Sorry, that was a really, really dense thing of me to say. Yes, of course it's decomposition. Yes, you're just breaking it down. Well done you guys, you're on it. Okay, the other type of reaction that can happen with alkenes is electrophilic attack. So this area, our double bond, the pi part of the double bond, is has got high electron density. There's 4 electrons in that space, but also the 2 electrons in the pi bond are above and below our sigma bond. They're in the p orbitals of the carbons, so they're quite diffuse, they're quite far away, they're quite available for attack, and therefore electrophiles, things that are attracted to areas of high electron density, things that are able to accept pairs of electrons, are very able to attack our double bond. So sigma is the single bond. It's end-to-end orbital overlap. Pi bonds are side to side orbital overlap. We're not actually going to go through pi bonds and sigma bonds in this session, I'm afraid, because otherwise we would run completely out of time. If you have a look back through our web classes though, I'm sure one of the ones we've done on YouTube is we've included content on sigma and pi bonding. What it is, I can't remember. It might be one on covalent bonding, maybe something to do with that. I think we've got it on one of our YouTube classes. Where did we get to? Yes, good. They do. Electron clouds overlap, but it's end-to-end orbital overlap. So the pi bond is electron rich. Oh, rich. And susceptible. So I can't spell susceptible. Oh, no, come on. Susceptible to attack from electron deficient species. So species, things that are able to accept a pair of electrons, i.e. electrophiles. That's it, looking good, guys. Yep, well done. Okay, so moving forwards, another thing that we can do is hydrogenation. What are we adding? If you were to guess, if you don't know, what are we adding to an alkene when it undergoes hydrogenation? If you're not sure, have a guess. What are we getting? What are we adding? And do you know what the reagents and conditions are? Well done, guys. We're adding hydrogen. So we're adding hydrogen. So what are the reagents and conditions that we need in order to add hydrogen? What are the reagents and conditions needed to add hydrogen? For hydrogenation, this is, rather than anything else. Good, heat and a nickel catalyst. Fantastic, well done. Heat and a nickel catalyst. Then there's a little bit of an application for Edexcel students only. We look at hydrogenation when we talk about saturated and unsaturated fats. So margarine is hydrogenated, unsaturated fats. Oh dear, what was that handwriting? Fats, i.e. oils. It's quite a thick oil, can be oils as well. Whereas butter is saturated. Okay, so that's one of the processes or things that happens that can happen with alkenes. This is hydrogenation, the addition of hydrogen across the double bond. So all we've done is broken that bond. Each carbon has accepted a hydrogen onto it to produce an alkane. We go from an alkene to an alkane. Hopefully that everyone's happy with that one. I'm just going to whiz on through in case, unless anyone has any major questions, to the next one. So symmetrical halogenation. What are we adding when we do halogenation? What are we adding when we do halogenation? And do you know any reagents or conditions needed for halogenation? Good, well done. Fantastic. We're adding halogens. Well done. We're adding halogens. So our halogens, like chlorine. So I'm going to call X. We do often notate halogens as X. So going to be like chlorine, bromine, or iodine. You're not likely to do anything other than chlorine, bromine, and iodine. But it has to be in X2. We need to be adding our diatomic halogen because that's what is necessary. Yes, you do have to do symmetrical halogenation for AQA. Yep, I'm afraid so. So symmetrical halogenation, because we're adding both atoms of halogen in the same way that we added both hydrogen atoms across the double bond. In this case, we add both atoms of the halogen across the double bond. So we end up with a halogen. I'll just put them in as X. Now, it doesn't matter where on here you put the halogens, as long as you've got one on each carbon, because this single bond can rotate. And because it can rotate, actually that halogen could be anywhere, could be on any of those, in any of those spots, as it were. So it doesn't matter where you put them. I'm going to put them both at the top, just for fun. Yep, good, well done. So we only really need to say the halogen. They add fairly readily across a double bond, and therefore we can use it as a test for halogen. Oh, that's fine. Yeah, it's interesting seeing information presented in a different way, isn't it? Because you go, oh, hold on, have I done this yet? And then when you look at the mechanism, you're like, oh yeah, I've done the mechanism, but I've never called it that before. And that's fair enough. So what's the test for alkenes then? Hopefully you did it at GCSE, but what's the test for alkenes? Oh, lovely. Really nice, guys. Fantastic. Bromine water. So our test for alkenes is bromine water. And then what would we expect to happen? Lots of you have said already, which is brilliant. So our add the alkene to bromine water, or add bromine water to the alkene. So I'll just say add them together. And the bromine water should go from orange to, from orange to colorless. The reason this is because Br2 in water is an orange color. Br2 in solution is an orange color. If you remove it from solution by adding it across a double bond, then it's no longer in solution, and our dihaloalkane is colorless as well in solution. So you get the removal of the orange color. So you get to see the color change from orange to colorless if there is an alkene present. Really nice, well done. Fantastic. So that means there must be a double bond present. Let's keep pressing on then. So for symmetrical electrophilic addition, whether or not that is our dihalogen or H2 or whatever, we have the same reaction mechanism. What's the catalyst, as it were, for this mechanism? And I don't mean actual catalyst. I mean, why, if I've got Br, for example, why does this reaction happen? What prompts this reaction to happen? I.e., what's missing from my diagram here that encourages an attack? So is the color, brown is the color for bromine, the liquid, not bromine water. So bromine, you can say, yeah, bromine is the, brown is the color for bromine, but bromine water is orange. Yeah, well done, good. Okay, good, well done, guys. So Sophie, you've got, that's a really good thing to have a connection for here with halogens. But in this case, the thing we're looking at is the dipole. We've got, it is induced. You can obviously have it, well, my brain's not working. Instantaneous dipole as well, but because you've got this high area of electronegativity, you've got this high electron dense area, it's probably going to induce a dipole in our dihalogen, in our molecule. So we will get an ever so slightly delta positive bromine and an ever so slightly delta negative. This is where the electrons have shifted ever so slightly towards one or other of the atoms. So they're ever so slightly got a slightly extra negative charge compared to the other bromine. And because the nucleuses of our bromines are positive, if you remove the electrons ever so slightly from the bromine, you're going to experience an ever so slight positive charge on one bromine. Exactly right. Yeah, lovely. So with that then our electrons, which are freely available, can be attracted to this area of positive charge. And that means we get the movement of electrons. And we should always try and get our arrow to go from a bond or a pair of electrons to wherever they're going. Now, they are a little bit lenient with where the arrows end up, but just make sure it's clear what it's bonding to, and don't stick the arrow far out in the middle of nowhere, because then no one will know. Good question, Khadija. Yes, most of the time you would lose a mark. They are looking for the dipoles here, unfortunately. Yeah, good question though. So this is an induced dipole. There will, like I said, there will be some instantaneous dipoles as well, but one of the reasons why this reacts quite well and quite quickly is because there is an induced dipole. And then we've broken the pi part of the double bond. We've still got the sigma bond, we've still got the single bond, but we've broken the pi part of the double bond. And therefore we have, now it doesn't matter which bromine you stick it on. We'll look at this a bit more in a couple of minutes, hopefully quickly. Yes, same as a temporary dipole, induced dipole is, no, sorry, where? I'm trying to think what we use the term temporary dipole for, because I'm so used to saying induced and instantaneous. It's caused by something. It's not random movement of electrons, if that helps. So an induced dipole is caused by something. It's caused by this high electron dense double bond, which pushes electrons away from one end. It might make slightly more sense if I just do my bromine downhill a bit, so that it's a little bit further away, so they're pushing the electrons away. I don't know if that helps. Yeah, so it's not just uneven distribution of electrons just randomly, it's induced, it's caused. That means that we end up with, what's this species called in the middle? What's that species called in the middle? Oh, thank you. Yes, I totally forgot. I was too engrossed in talking about the how to draw arrows. Thank you. Well done. Good spot. KK, well done. Yes, we needed to show that bond breaking. Otherwise, it's just randomly broken for no apparent reason. Good. Our bromine only wants to have one bond. So if it's going to form a bond with a carbon, it needs to get rid of its bond with the other bromine. So then you end up with your bromide ion. It is called a carbocation. Well done. And then we've got a very obvious attraction between the positive carbocation and the negative bromide ion. So there is definitely going to be a bond happening there, because they're going to be attracted to each other. Again, we show movement from a pair of electrons to wherever it's going to form our dihalogen. Like so. Br2 liquid. So you can do both. With bromine water, we don't need to have pure bromine. It would be silly to have pure bromine, because you'd have to have an exact amount of bromine, or at least very, very small amount of bromine. So you'd have to add the bromine to the alkene, and normally we would add an alkene to a bromine water. So if you have bromine water, you can at least be very, very dilute. If you have liquid bromine, you could be there forever adding alkene to work out whether or not it goes colorless or not. So with our test for alkenes, bromine water, in this case, you can have bromine liquid, Br2, or you can, wait, if you have, I think if it was a liquid here, if it was bromine water, bromine dissolved in water, you would run the risk of having side products actually. So not in this case. What do you think? Is this a primary or a secondary cation? What do we reckon? Yes. Sorry, I can't read my chat. Kangol, yeah, I agree. Then there might be some side products. So we can't have bromine water in this one, but we would in the other one. We could have either in the other one, but more likely bromine water. In this one, you need to just have pure bromine. So this is a primary. Yeah, this is a primary because our carbocation carbon is only attached to one other carbon. So it is a primary cation. Primary carbocation. But it can't form anything else. We can only form a primary carbocation here. It doesn't matter which carbon we bond our first bromine to. It's always going to be a primary carbocation. Why does it start with positive bromine and not negative bromine? Good question. Because this double bond is an area of high electron density. It's negative. Electrons are negatively charged. So it is going to be attracted to a positively charged bromine, not a negatively charged bromine. Think about magnets. If you point north and north to each other, they repel each other. That delta negative bromine is not going to want to go anywhere near a very high electron dense double bond. So it's going to be attracted to a positive charge. What would happen if this is an alkyne? Similar stuff, I think. You would just break the triple bond first, and I think it'd be exactly the same. You just end up with an alkene at the end instead of an alkyne. Instead of an alkane, sorry. Good. Right. How is everyone feeling about that? We are running late. I'm so sorry that I talk too much. We talk too much. But I'd rather you guys ask you questions and you guys get the most out of these sessions than me just talk at you. So give me a number or a smiley face. Let me know how you're feeling about this. Positive, all right, it's okay, or oh my gosh, no. So give me a 1 or a happy smiley face, and 2 if oh no, or 3, oh my gosh, no, this is horrible, I hate it. Fabulous. Okie dokie, awesome. That's lovely. Good. Okay, we haven't left anyone too far behind then. Okay, so we're gonna skip through these exam questions just so we get onto the content of the next ones, but please feel free to have a go at it in your own time. We've basically already done these questions just in theory, so use your notes that we've just made to have a go at these. So this is looking at reaction 1, going from ethene to ethane, so have a think about what you're going to need there. The second question is compound X, so we've got ethene and we're adding bromine, so what are we going to add, what are we going to end up with, and then can you draw it? And then this final question is suggest a mechanism of 2-methylpropene with bromine. So we're about to have a look at this now, so we'll come back to this question in a minute perhaps. Matthew, this one, well, this we're about to look at because we're about to look at Markovnikov rules, so we're literally just about to do these types of questions. So we are, don't you worry. Okay, so part 2, Markovnikov rules and or major minor product formation, depending on which exam board you're in. So Markovnikov rules talks about carbocations having different levels of stabilities. We looked at carbocations being that intermediate product which is a carbocation. It's a carbon with a positive charge, carbon, cation, positive charge. So positively charged carbon. Which is most stable and which is least stable? Do you know which is most and which is least stable? We've got, this is a tertiary carbocation because it's got 3 carbons attached to our central carbon. This middle one is a secondary carbocation because the carbocation has 2 carbons attached to it. And this, oops, wrong one. This right-hand one is a primary carbocation because the carbocation carbon has 1 carbon attached to it. So which is most stable, which is least stable? So primary, secondary, or tertiary, we've got some different ones. We've got some different answers. So let's think about what these groups are useful for, and then we can decide who's correct. Alkyl groups, alkyl being alkane, like an alkane, but the "-ile" bit means it's an additional group. So an alkane additional group, i.e. like methyl, so like a CH3, which is what the end of this, what the end of a skeletal structure represents. If it's not got anything on it, it means it's a methyl group. So this tertiary carbocation here has got 3 methyl groups on it, and they, fabulous. I've seen lots of really nice, or a couple of really nice suggestions. They stabilize the group. They are, if you're Edexcel, they are electron releasing. You can also talk about them in AQA, we talk about them having a positive inductive effect, but they are electron donating groups. We get this donation of electrons because neither carbon nor hydrogen are very electronegative. So they don't have much pull on their electrons. So if there is a positive carbon in the center of this molecule, then their electrons are very able to go and stabilize that positive charge. They're going to be attracted to the positive charge, and in doing so, they spread out the positive charge or minimize that positive charge to allow it to be much more stable. There isn't this highly charged central, very specific positive charge. It's spread out and it's reduced by this inductive effect. And because there's 3 whole groups, it is super stable. So yes, OCR, we talk about it spreading out the charge. So let's write those down. So OCR, we spread out the charge. So if the electrons from the CH3 move ever so slightly towards the carbocation, or the carbocation carbon, then our CH3 might become ever so slightly delta positive, but the carbocation, which has a full positive charge, becomes less fully positively charged, and becomes ever so slightly less positively charged because it's being cancelled out by the electrons. So OCR, we say we spread out the charge. AQA, we talk about having a positive inductive effect, as in it's donating electrons, positive inductive effect. And then Edexcel. Oh my gosh, I can't spell Edexcel. Let's try that one again. Edexcel. There we go. We talk about the groups being electron releasing. Now, to be honest, you can use most of these words in any exam board and you would still get most of the marks, unless you've said it wrong. Just look at the ones that they want you to use. So this is the most stable. Our tertiary carbocation is the most stable, and therefore our end one is the least stable. I am going to have to disappear in a minute, which is really rubbish. So we're not going to have time to do these exam questions either. Therefore, it's most likely that a reaction will proceed through the most stable carbocation. So let's just have a look at this one. So if we have, so this is basically answering the previous question. If we have a propene, for example, which has got, or as we had there, 2-methyl. Actually, I don't know what we had there. So if we have propene, our intermediates can either be with our carbocation on the left-hand carbon, and our, oops, I've done that at an angle for some reason. So what am I going to add? Oh gosh, sorry, I pressed the button. So in this case, I'm adding HBr. So if I add my hydrogen on to this side, I'm going to end up with a positive carbocation on the left hand, on the primary. That's a primary carbocation. If I add my HBr and my hydrogen this time adds to the other carbon, so I end up with a secondary carbocation, CH3, because my carbocation is attached to two carbons, sorry. So that's a secondary carbocation. I'm going to end up with, this will be my major product, and this will be my minor product. My bromine will add there in this one. I'm scribbling now because I'm so out of time. I'm really sorry, guys. I am going to have to disappear in a second. That last 10 minutes just absolutely flew by. So our major product at the bottom is because it goes through the secondary carbocation, and the minor product goes through the primary. What did I say? Tertiary, secondary carbocation, and the minor product goes through the primary. Primary being least stable out of these two. This one being most out of these two stable. Oh, sorry guys. Right, I'm just gonna whiz on to the last slide. So hopefully this has been useful. We didn't get to do that last exam question or those last exam questions, so I apologize. But we have looked at the Markovnikov rules, we've looked at double bonds, and we've looked at our mechanisms. They're all very similar. These are our upcoming web classes, so please feel free to go and have a look at those and set yourself a reminder. We've got physics and then biology. If you're interested in our Snap Revise courses, I'm just going to super quickly show you the courses. So we've got loads available. We've got our revision guides, we've got bite-sized teaching videos, we've got smart quizzes that keep you up to date with what you do and don't know. We've got where's my screen gone? There. We've got exam walkthrough videos that talk you through different exam boards. We've got predicted exam packs where we've come up with questions that we think might be asked. We've got condensed revision guides, loads. We've got loads and loads of content on here, as well as the web classes and stuff as well. So please, so this is our course. As part of the course, you can have your web classes, which means we get drop-ins and web classes like the one we've just done, where you can have a look at what we're going to go through, plan your week, come to as many or as few web classes as you want. You can also, they're all recorded, so you can look at them at any time. But one of the things we also have on the website, please go and have a look, is our flashcards. They are super condensed, super precise, really, really easy to use flashcards, but we've got loads and loads of content on there. So if you're interested in that, let me just come back off that. So I've just whiz talked through that because I'm way out of time. If you're interested in that, then please feel free to use the code, which I will show you now, although it's being really slow. Oh no. Oh no, my thing is frozen. There we go. So, oh, I don't know if you guys can see that. Oops. Oh, no, it's just shut it down. There. So please feel free to use the code back to school 21 to get 25% off your first month subscription payment if you feels like your sort of thing. Hope you've had a useful session. Really sorry I'm gonna have to go. If you have any other questions, please drop them. Please drop an email to hello@snaprevise.co.uk and we'll try and get back to you with as much information as we can. Please feel free to look at some of these other web classes, and I hope to see you very soon on a web class and or on our website. So have a lovely rest of your weekend, guys, and I will see you very soon. Bye. Thanks, guys.